My name's Graham Finch. I'm building enclosure engineer with RDH Building Engineering in Vancouver, British Columbia. So RDH has been doing a lot of research in the building enclosure field. In recent years, we've been looking at improving the energy efficiency of buildings and also different strategies to better insulate buildings. During the construction of these roofs, we took samples of insulation from site, cut them up, and measured them in the lab to measure the apparent or effective R value they had at certain temperatures. First, looking at standard conditions, which the industry uses and which most specification sheets produce. But we also looked at what happens when it's really cold or really hot. If you look at most roofs, when the sun comes out, they get quite hot. So the R value of that insulation changes, especially at the surface, as the temperature increases. Within the energy model, we took the default material properties and modified them to reflect the laboratory and field monitoring conditions that we measured. We then modeled the 3 different insulation assemblies and roof membrane colors for a total of 9 different assemblies within the 8 climate zones in North America to look at what would the optimum insulation assembly and membrane color be for your climate and your building type. What we found was really interesting. We found how the R value of the insulation products would change with temperature, but also with the polyiso, how it changed between that first year and that 4th year of that age sample we had. The heat flow measurements are the direct measurement of the heat loss or gain through the different insulation assemblies. The results we found confirm the findings we found in the laboratory with that how the different insulations change R value with temperature. What we're still missing is the reality that some insulation products don't behave the way they're stated on a spec sheet. I mean, you only really need insulation when it's really cold or really hot. You know, having a insulation spec that says, all right, this is the R value at room temperature, when you don't have any heat loss, isn't actually that useful to you. You need to know how that insulation behaves at winter conditions, summer conditions, and then depending on where you are, what climate you're in, that's going to help you decide what insulation is most appropriate or how much insulation. When we put in the climate-dependent R values into the energy model, we got an accurate representation of what roof assembly would be more appropriate for each climate. When we looked at the default parameters, we got a different answer, which told us that it was important to look at this. We found that actually accounting for the climate-dependent R value made a difference in our recommendations for a type of roof assembly and also membrane color. For energy modelers, see this as an advancement of the technology, understanding more about how insulation performance affects overall energy use in the building. By accounting for climate-dependent R values, you get a true representation of the heating and cooling season, how much heat flow occurs through different assemblies, and a more accurate one so you can better predict the actual energy use in a building. For building owners, where cost is often a concern, it's about making sure their designers and architects are using the correct inputs into their energy models, correct design decisions, and all this based on correct assumptions for the thermal performance of their insulation, which comes from that climate-dependent R value. Given what we know about climate-dependent R value and the impact it has on the thermal performance of building enclosure assemblies, something we hope will make its way into energy codes to result in better building enclosure design. At the end of the day, this means more predictable and energy efficient performance for the life of their building.